Public Exam Review for Advanced Math 3200, Unit 3, Chapter 2 on Radical Functions. In this presentation, we will look at the square root of quadratic functions of the form y equals the square root of ax squared plus bx plus c. Here we will focus on sketching the graph of y equals the square root of f of x, given the graph of y equals f of x as the square root of ax squared plus bx plus c. We will explain strategies for graphing the square root function given the graph of the original function, and compare the domains and range of the original function and the square root function, explaining any differences. If f of x is equal to a negative x squared plus 16, then sketch the graphs of y equals f of x and y equals the square root of f of x on the same coordinate plane. If the function f of x is equal to a negative x squared plus 16, we should recognize it as the graph of a parabola that opens downward, because of the negative in front of the x squared term. As well, the vertex of this parabola is located at 0 and 16. So we have 0, 16 as the vertex of the parabola, and the parabola opens downward. Next, it is important to determine the x-intercepts. And we do so by letting f of x equal 0. So then we have 0 is equal to a negative x squared plus 16. Bringing all the terms to the left-hand side results in x squared minus 16 is equal to 0. The left side can be factored as a difference of two squares. X plus 4 times x minus 4 is equal to 0. One x-intercept occurs when x plus 4 equals 0 at x equals a negative 4. And the other x-intercept occurs when x minus 4 equals 0 at x equals 4. These will also provide us with the coordinates of one set of invariant points for the original function and its square root. Knowing what the x-intercepts are and the vertex of the parabola, you can now sketch the graph of the original function. Note that the vertex is a maximum point on this graph. That is important to note because it will also help us to determine the maximum point of the square root function, which helps us to determine the range. So let's look at a few values in the table of values. When x is a negative 4, f of x is equal to 0, and the square root of 0 is 0. So the coordinate negative 4 and 0 will also be a point on the graph of the square root function. Similarly, when x is equal to 4, f of x is equal to 0, and the square root of 0 is 0. So another point on the square root graph is located at 4 and 0. If you locate the vertex, when x is equal to 0, y or f of x is equal to 16, and the square root of 16 is equal to 4. So the point 0, 4 lies on the graph of the square root function. We know that when the values of y are greater than 0 but less than 1, that the square root function graph will always be greater than the original function. Keeping that in mind enables us to sketch the graph of the square root function as follows. So between 0 and 1, the graph of the square root function is greater than the graph of the original function. So now we can state the domain and the range of the square root function. Note for the domain, when you literally put your finger on the x-axis, the smallest value that x will be is a negative 4, and the maximum value that x will be is a positive 4. So we state the domain as all values of x such that negative 4 is less than or equal to x, which is less than or equal to a positive 4, and x belongs to the set of real numbers. Similarly, to determine the range of the square root function, the smallest value that y will be is 0, and the maximum value that y will be is 4. So the range is all values of y such that 0 is less than or equal to y, less than or equal to 4, and all values of y belonging to the set of real numbers. Next, we will algebraically determine the coordinates of any invariant points that exist. The invariant points will always occur when f of x is equal to 0. Those were the x-intercepts that we originally determined. So one invariant point is at -4 and 0, and the other one is at 4 and 0. Another set of invariant points occur when f of x is equal to 1, because when y is equal to 1, the graph of y equals the square root of f of x and the original function f of x are equal to each other. So when f of x is equal to 1, we have a negative x squared plus 16 is equal to 1. Negative x squared is equal to 1 minus 16. So we have negative x squared is equal to a negative 15. Therefore, x squared is equal to a positive 15, which means that x is equal to plus or minus the root of 15. So the other set of invariant points will occur at a positive root 15 and 1, and at a negative root 15 and 1. To locate these points on the graph, there would be a negative the root of 15 and 1, and this one over here would be at a positive root 15 and 1. Those are the exact coordinates of the invariant points. In the next example, if f of x is equal to 1/2 x squared plus 1/2 x minus 6, then sketch the graphs of y equals f of x and y equals the square root of f of x on the same coordinate plane. In the previous example, we had a parabola that opened downward. In this example, notice that the parabola will open upward. So we have f of x equals 1/2. The positive 1/2 in front of the x squared tells us that the parabola will open upward. In this case, because the parabola is in standard form, we need to use a special formula to determine the coordinates of the vertex of this parabola. The vertex will occur when x is equal to a negative b over 2a. This formula will help us to get the x-coordinate of the vertex. The value of b here is given to be a positive 1/2. So we have negative 1/2 over 2 times a half. So that leaves us with negative 1/2 over 1, which is just equal to a negative 1/2. The y-coordinate of the vertex can be determined by substituting in a negative 1/2 into the original equation to determine the value of y. So we have 1/2 times a negative 1/2 squared plus 1/2 multiplied by a negative 1/2 minus 6. That leaves us with 1/2 multiplied by 1/4 minus 1/4 minus 6. So then we have y equals 1 over 8, and we can express the other two terms with a common denominator of 8. So negative 1/4 is the same as a negative 2 over 8, and a negative 6 is the same as a negative 48 over 8. When you work that out, you get the value of y to equal a negative 49 over 8. So the exact coordinates of the vertex of this parabola are at negative 1/2 and a negative 49 over 8. In order to locate that on the graph, we have to write it as a decimal approximation. So we have a negative decimal 5, and then 49 divided by 8 is approximately negative 6.125. So negative 1/2 and negative 6.125 is approximately right here. So that would give us a minimum point on the graph of this parabola. Similarly, we need to determine the x-intercepts for this graph. So in order to get the x-intercepts, we will let f of x equal 0. So then we have 1/2 x squared plus 1/2 x minus 6 is equal to 0. In order to get rid of all the fractions, we can multiply both sides of the equation by 2. That would result in x squared plus x minus 12 is equal to 0. This equation is now factorable. We have two factors of a negative 12 that have a sum of a positive 1. So the factors would be x plus 4 multiplied by x minus 3 to equal 0. Therefore, we have x plus 4 equals 0 when x is equal to a negative 4, and that will give us one x-intercept on our graph. And the other one occurs when x minus 3 equals 0, and that's at x equals a positive 3. Knowing the x-intercepts of the graph of this parabola as well as the vertex, we can now sketch the graph of this parabola as follows. So that represents the graph of y equals f of x. We will pick some points on the graph of this original function in order to determine the coordinates of the graph on the square root function. So when x is a negative 4, f of x is equal to 0, and the square root of that is 0. When x is a positive 3, f of x is equal to 0, and again the square root of 0 is 0. So these coordinates will also provide us with the set of invariant points for this function. When x was equal to a negative 1/2, f of x was equal to a negative 49 over 8. Notice that the square root of a negative number is not defined. That will be true for any values of f of x that are less than 0. So the values between negative 4 and a positive 3 will not provide us with any points on the graph of the square root function because we cannot take the square root of a negative number. When you look at the other set of invariant points, they will occur when y is equal to 1. So you can locate those points on your graph. And remembering that the graph of the square root function is greater than the graph of the original function, you can now sketch the graph of the square root function as follows. The square root function is greater in the interval between 0 and 1. So that's a sketch of the graph of y equals the square root of f of x. We can now state the domain and the range of the square root function. It's all values of x such that x is less than or equal to a negative 4, or x is greater than or equal to a positive 3, and x belongs to the set of real numbers. The range, on the other hand, are all values of y such that y is greater than or equal to 0, and y belongs to the set of real numbers. There is no maximum value for the range. In order to determine the coordinates of the invariant points, again they will occur when f of x is equal to 0. That would be at our x-intercepts. So one set of invariant points occurs at negative 4 and 0, and the other set is at 3 and 0. Another set of invariant points occur when f of x is equal to 1. So then we have 1/2 x squared plus 1/2 x minus 6 is equal to 1. If you bring the 1 over to the left-hand side, you have negative 1/2 x squared plus 1/2 x minus 7 is equal to 0. We can eliminate the fractions by multiplying both sides of the equation by 2, where we get x squared plus x minus 14 is equal to 0. In order to determine the values of x for which that happens, there are no factors of a negative 14 that have a sum of a positive 1. So in this case, we would have to rely on the quadratic formula in order to determine the exact coordinates of the invariant points. So the quadratic formula is stated as follows. And we can substitute in the values of A, B, and C into the formula to determine the value of x. So we have negative 1 plus or minus the square root of 1 squared minus 4 times 1 times C, all divided by 2 times 1. X equals a negative 1 plus or minus the square root of, that becomes 1 plus 56, all divided by 2. As a result, when we simplify that, we have x equals a negative 1 plus or minus the root of 57, all divided by 2. So another set of invariant points will occur at negative 1 plus the root of 57, all divided by 2 and 1. And the other one will occur when x is a negative 1 minus the root of 57, all over 2, and the y-coordinate would have to be 1. So to illustrate those points on the graph, this would be at negative 1 minus the root of 57, all over 2 and 1. And this invariant point here would occur at negative 1 plus the root of 57, all over 2, and a positive 1. Let's look at some examples. For the function f of x equals x squared plus 4x minus 5, what is the domain of the square root function? Y equals the square root of f of x. Notice that the domain of this function is dependent upon the location of the x-intercepts. The graph of this parabola represents one that opens upward. The parabola opens upward. So in order to determine the domain of this function, we need to know the location of the x-intercepts. So the x-intercepts here will occur when f of x is equal to 0. So we have x squared plus 4x minus 5 equals 0. To factor that, you have the factors of a negative 5 that have a sum of a positive 4. X plus 5 times x minus 1 equals 0. So one x-intercept occurs when x is equal to a negative 5, and the other x-intercept occurs when x is equal to 1. Negative 5 and a positive 1, and you know that your parabola opens upward. I'm just sketching that for now. It's not important that we sketch the graph. However, we can determine the domain of the original function. If you go to where y is equal to 1, and the points where y is equal to 0, remember that the square root function graph is always greater during that interval. So the graph of your square root function will look something like this. That's the y equals the square root of f of x. Notice that the domain here represents all values of x that are less than or equal to a negative 5, or the values of x that are greater than or equal to 1. So this answer corresponds with C as the multiple choice answer. In the next example, we are asked which graph represents y equals the negative, the square root of f of x. So what we need to do, first of all, is determine what the graph of y equals the square root of f of x is, and the negative represents a vertical reflection in the x-axis. So once again, the original function represents a parabola that opens upward. So we need to determine the x-intercepts again by letting f of x equal 0. So we have x squared plus x minus 6 equals 0, which can be factored as x plus 3 times x minus 2 to equal 0. X plus 3 equals 0 when x is equal to a negative 3. X minus 2 equals 0 when x is equal to a positive 2. This question has a little twist to it. So when you look at the graph of the original parabola, it will occur when x is a negative 3 and when x is equal to a positive 2. The parabola opens upward. So there's the graph of our parabola. When you go to take the graph of the square root function, you locate where y is equal to 1 and where y is equal to 0. And these give us the coordinates of the invariant points. So the green graph that you see here is the graph of y equals the square root of f of x. But now what we need is a reflection in the x-axis. So now these points have to be flipped about the x-axis, which will be located as follows. When it's reflected in the x-axis, the graph will look something like that. So that will be y equals minus the square root of the y equals minus the square root of f of x. So that graph then corresponds with, I'm looking for x-intercepts at negative 3 and a positive 2. So the answer for this question corresponds with C as the multiple choice answer. So the key thing here is to notice that the negative is in front of the square root sign. So that represents a vertical reflection in the x-axis. In example 3, we are asked to determine the domain and the range of y equals the square root of a negative 1/2 x squared plus x plus 12. Note the original function f of x is equal to a negative 1/2 x squared plus x plus 12. This represents a parabola that opens downward. In order to determine the domain and the range for this square root function, we need to locate the x-intercepts again, and you will also need to locate the vertex of this parabola. Since it's a maximum point on the parabola, it will also be a maximum point on the square root function. So the first thing we can do then is determine the coordinates of the vertex by using the formula x equals a negative b over 2a. Here we have x equals a negative, b is 1, all divided by 2 times a negative 1/2. That's a negative 1 divided by negative 1, so the x-coordinate of your vertex here is at 1. The y-coordinate can be found by substituting in 1 for x into the original equation. So we have y equals a negative 1/2 times 1 squared plus 1 plus 12. Y equals a negative 1/2 plus 13, which is the same as 26 divided by 2. So the y-coordinate here is equal to 25 over 2. The coordinates of the vertex then are at 1 and 25 over 2. Next, we will determine the x-intercepts of this graph. The x-intercepts occur when f of x is equal to 0. So we have a negative 1/2 x squared plus x plus 12 is equal to 0. Multiplying both sides of the equation by negative 2 helps us to eliminate the negative coefficient of the x squared term as well as any fractions that exist. So we have x squared minus 2x minus 24 is equal to 0. This can be factored as x minus 6 times x plus 4 is equal to 0. So x minus 6 equals 0 when x is equal to 6, and x plus 4 equals 0 when x is equal to a negative 4. Let's sketch the graph of this parabola so that we can clearly identify the domain and the range of the square root function. As you know, 25 divided by 2 is approximately 12.5. So the coordinates of the vertex will be at 1 and 12.5. So we have 1. Let's pretend that 12.5 is here. And that's a maximum point on the graph. 2, 3, 4, 5, and 6 gives us one x-intercept. And -4 will give us another one. And this parabola will open downward. Now, to locate the square root function graph, we go to where y is equal to 1 and where y is equal to 0. And you have 4 invariant points on this graph. Notice that the maximum value, if f of x is equal to, and I'll just set up a little table of values here to illustrate this part, but if f of x, the maximum point is at 12.5, then the square root of f of x, the square root of 12.5 is approximately 3.56. So that would be roughly about here. So we'll just, that should be 1. Let me just move the coordinates of that point. It should be at 1 and approximately 3.54. I said 5.6, but it's supposed to be 5.4. And that would represent a maximum point on your graph. So the square root function graph is going to look something like this one. Remember that the square root graph is greater than the graph of the original function for values of y between 0 and 1. So now we can clearly state the domain and the range of your square root function. The domain of the square root of f of x will be all values of x between -4 and a +6. So we write it as -4 is less than or equal to x, less than or equal to 6, and x belongs to the set of real numbers. The range, on the other hand, are all values of y that are greater than or equal to 0, but less than or equal to the square root of 25/2, which is approximately 3.54. And y belongs to the set of real numbers. In the last example, if f of x equals a -x² minus 2x plus 15, sketch the graph of the original function and the square root function on the same grid. State the domain and range of the square root function and determine the coordinates of the invariant points. So we have, here we have the graph then represents a parabola that opens downward, -x² minus 2x plus 15. It represents a parabola that opens downward. We need to locate the vertex of that parabola by using x equals a -b/2a. That's a standard formula we use to find the vertex of a parabola in standard form. So this time the value of b is a -2, so we have minus a -2 over 2 times a -1. That leaves us with a +2 over a -2. The x-coordinate of the vertex is at -1. The y-coordinate of the vertex, and you have to be careful here with the signs, it's minus a -1 squared, -2 times a -1 plus 15. So a -1 squared is a +1. With a negative in front, it's a -1. Plus 2 plus 15. So the y-coordinate of the vertex is at 16. So the vertex here is at -1 and 16. Note that the square root of that if that's the point on f of x, then the corresponding point on the square root function graph will occur at -1 and the square root of 16, which is 4. So we might as well take care of that right now. That will be a point on the square root graph. So now, let's go and determine the coordinates of the x-intercepts here. So the x-intercepts for this function will occur when f of x is equal to 0. So we would have 0 is equal to a -x squared minus 2x plus 15. Bringing all the terms to the left-hand side, we have a positive x squared plus 2x minus 15 equals 0, which factors to be x plus 5 times x minus 3 equals 0. So one x-intercept will occur at x equals a -5, and the other x-intercept occurs when x is equal to 3. To represent that on the graph, we have a -5 and a positive 3. And now we could sketch the graph of the original function. So that represents the graph of y equals f of x. To get the graph of the square root function graph, we have to go where y is equal to 1. And knowing that the square root function graph is always greater, and remember that the point -1 and 4 lies on the graph of the square root function graph. So we can sketch the graph of the square root function as follows. And now we can easily state the domain and the range of the square root function graph. The domain of the square root function are all values of x such that -5 is less than or equal to x, which is less than or equal to 3, and x belongs to the set of real numbers. The range of the square root function graph are all values of y that are greater than or equal to 0, but less than or equal to 4, and y belongs to the set of real numbers. Lastly, what we need to do is to determine the coordinates of the invariant points. So the invariant points will occur when f of x is equal to 0. That would be at our two x-intercepts, a -5 and 0, and the point 3 and 0. Another set occurs when f of x is equal to 1. So then we have a -x squared minus 2x plus 15 is equal to 1. So then we have a -x squared minus 2x, bring the 1 over, results in a positive 14 is equal to 0. Multiplying throughout by -1, we have x squared plus 2x minus 14 equals 0. And the exact value of x there can only be determined, again, by using the quadratic formula. So we have a minus b plus or a minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So we have x equals a -2 plus or a minus the root of, that becomes 4 plus 4 times 14 is 56, all divided by 2. Here we have x equals a -2 plus or a minus the root of 60, all divided by 2. And 60 can be reduced into, the square root of 60 can be reduced into simpler radical form. 60 is the same as 4 times 15, all divided by 2. So we have a -2 plus or a minus 2 root 15, all divided by 2. So finally we have our value of x to be a -1 plus or a minus the square root of 15. So one invariant point will occur at -1 minus the root of 15 and 1, and the other one will occur at -1 plus the root of 15 and 1. These points can also be illustrated on your graph. This one will be at -1 plus the root of 15 and 1, and this point right here would be at -1 minus the root of 15 and 1. As a summary then, you can use the values of f of x to predict values for the square root function and to sketch the graph of y equals the square root of f of x. The key values to consider are f of x equal to 0 and f of x equal to 1. When f of x is equal to 0, that will also provide us with the x-intercepts on the graph of your square root function graph, as well as the original function. And it provides us with the x-intercepts as well as one set of invariant points. So these points here can also be used to determine the invariant points as well. So this one, f of x equals 0, it gives us the x-intercepts, and both of them together will provide us with the invariant points, which are points that are common to both the original function and the square root function. So the domain of y equals the square root of f of x consists of all values in the domain of the original function for which f of x is greater than or equal to 0. The range for y equals the square root of f of x consists of the square roots of all values in the range of f of x for which f of x is defined. Remember that when f of x is less than 0, that you cannot take the square root of a negative number using the real number system. The y-coordinates of the points on the graph of y equals the square root of f of x are the square roots of the y-coordinates of the corresponding points on the original function. So the relative locations, just remember that the square root function graph is always greater than. The square root function graph is always greater than the original function graph for values of y that are greater than 0 but less than 1. That piece of information helps us to sketch the graph. So in this case, when f of x is less than 0, that means that the graph of the original function is below the x-axis. The graph of the square root function is undefined because, again, you cannot take the square root of a negative number using the real number system. When f of x is equal to 0, when f of x is equal to 0 and when f of x is equal to 1, that's where the two graphs will intersect on the x-axis. The two graphs will intersect. And then when you have when f of x is between 0 and 1, the graph of your square root function is above the graph of y equals f of x. I find that to be an important piece of information to remember when sketching the graph. And when f of x is greater than 1, the graph of the square root function is below the graph of the original function. If you have any questions related to this content, please pose your question in the question forum and we will be happy to answer it for you. Thank you.